Okay. Our next example is about Philip the polynomial, part 1. Philip is a function. F of x is equal to x to the fourth minus 4x cubed plus 4x squared. We want to find whether this function is increasing or decreasing. So naturally our first step is to find the first derivative. The first derivative, whether it's positive or negative, will tell us whether the original function increases or decreases. Using the power rule, we find that the first derivative is 4x cubed minus 12x squared plus 8x. This function is already more complicated than the quadratic we encountered in our first example. Our second step will be to find the critical points, which means that we need to set this first derivative equal to 0. This is where your algebra techniques of factoring will come in handy. We notice also that the first derivative is never going to not exist. So we aren't going to find any critical points except where f prime is equal to 0. When we factor out of 4x, which is what each of these terms has in common, we find we're left with an x squared minus 3x plus 2. This is a typical sort of factoring problem that we've encountered before. When we factor this out, we get 4x times x minus 2 times x minus 1, which will then set equal to 0. When we set each of those pieces equal to 0, we get x is equal to 0, x is equal to 1, and x is equal to 2. 3 critical points for us to work with in this problem. Our third step, you guessed it, we're going to use a sign test to find out where f prime is bigger than 0, and so forth. This sign test is a little more complicated, so I'll lead you through this. Remember our critical points were x is equal to 0, x is equal to 1, and x is equal to 2. And here's our factored form for our derivative right here. We need to test 4 different slots here. The first slot will be when x is less than 0. For example, if x is equal to negative 1. When we plug in negative 1 into our derivative, we're going to find that this first piece, the 4x, will produce a negative number. Our second piece, negative 1 minus 1, will also be negative. And our last piece, negative 1 minus 2, will also be negative. We've got 3 negatives here, so overall a negative times a negative times a negative is a negative. We'll put a negative right here. And remember, our sign can only change if we are at a critical point, which may be where the derivative is equal to 0 or the derivative is undefined. Okay? In between 0 and 1, we want to test x is equal to 1/2. And remember, we're only concerned about whether our derivative is positive or negative for each of our factors. When we plug in 1/2 into the 4x portion, we're going to get a positive number, a negative number here, and a negative number here. Altogether, we've got 2 negatives. Multiplied together will eventually get us a positive. A number in between x is equal to 1 and x is equal to 2 is x is equal to 3/2. When we plug in 3/2 into this, we're going to get a positive number, and a negative number. Altogether, that's 2 positives and a negative, which gives us a singular negative. Then between 1 and 2, our derivative is going to be negative. A number bigger than 2 would be something like x is equal to 3. That's supposed to be a 3 there, but it's been smudged. When we plug in 3, we're going to get a positive, and a positive. 3 positives all together will make a positive, so we end up with a sign test that looks like this. This sign test should make sense if you remember from pre-calculus. You notice that the sign is changing at each of our critical points. And the reason for that is the multiplicity on each of these roots is odd. In fact, they're all to the power 1. For x to the first will mean we've got a sign change at x is equal to 0. X minus 1 to the first will mean that we have a sign change at x is equal to 1. And there's also a sign change at x is equal to 2 because it is raised to the first power and has multiplicity of 1. Odd multiplicity will mean that we change signs. Even multiplicity would mean that we keep the signs the same. For example, if this were an x minus 1 squared, we end up with no sign change at x is equal to 1. Now, our conclusions. Looking at our sign test, we find that f prime is bigger than 0 on the intervals 0 to 1 and 2 to infinity, so f increases on those 2 intervals. F decreases on the intervals negative infinity to 0, and 1 to 2, because f prime is less than 0 on those intervals. Okay, notice that we do have open brackets here. We're not concerned at this point with what's going on at x is equal to 1 or x is equal to 2 or x is equal to 0. They're not included as part of our increasing or decreasing because the derivative is 0 at those points.